we would like to move to the technical talk. So the first presentation is by Yosang Jeong in KISTI. So the title is a high performance simulation of quantum transport using Manycore computing. So you have 30 minutes, including the QA. So please keep around 5 minutes for QA. And so please start to share your screen. So Yosang.
Yes.
Okay. Yeah, please start if you possible.
Yes. Hi, this is Yosang Jeong from KISTI, and I'm going to present our study, the high performance simulation of quantum transport using Manycore computing. First of all, in order to perform the quantum transport simulation for nanowire structure, we need to use the non-equilibrium Green's function approach. And through this NEGF approach, results such as transmission, local density of states, and charge can be obtained. And I'm not a physicist, so I'm not sure exactly what this means, but I know that the NEGF approach involves inverse matrix computation, and it takes a very long time to compute. In the NEGF approach, the recursive Green's function algorithm is used to perform the matrix inversion instead of traditional inverse matrix computation. This RGF algorithm performs the matrix multiplication of, this RGF algorithm performs the multiplication of submatrices of a system matrix in recursive manner. And this algorithm evaluates not the entire inverse matrix, but the parts of inverse matrix, because the physics of transport behaviors can be obtained with the parts of inverse matrix. So RGF algorithm can save huge computing cost compared to the traditional way, but it is still most time-consuming part of NEGF approach. So we proposed several technical strategies for accelerating our in-house code Q and the RGF-based NEGF solver using KNL and GPUs. Let's take a quick look at the RGF computation process. The RGF algorithm consists of the 4 computational steps. The whole computing process of RGF can divide into 2 regions, the top and bottom half of the system matrix. And the computation is each region is allocated to a single MPI process. And the computing load of a single MPI length is processed in parallel with OpenMP threads. And as we can see, all steps of the RGF algorithm perform the submatrix multiplication. But the number of multiplication in step 3 is much bigger than in the other steps, because the step 3 computed the half of off-diagonal matrices. So we need to focus on the step 3. Let's think about the computing cost of step 3 and the size of nanowire structure to be simulated. The nanowire structure consists of multiple atomic unit cells. The transport happens along the x direction. The x-uses, which means the number of unit cells along the x direction, is related to the number of diagonal submatrices. And YZ-uses, which means the number of unit cells on the YZ plane, is related to the size of each submatrix. Of course, as the size of the nanowire structure grows, the number of computation increases in all steps. However, unlike other steps, in step 3, the number of submatrices to be computed increases extremely. As shown in this figure, as the XUC increases, we can see the number of off-diagonal, the orange dot increases non-linearly. And the size of each Each off-diagonal submatrix is also increased non-linearly. In conclusion, the performance optimization for step 3, precisely the complex number matrix multiplication, is essential to improve the performance of RGF algorithm. So we applied several techniques to improve the performance of complex number matrix multiplication. The first technique is data restructuring. In many cases, a complex number is represented with a structure that has a real and imaginary number as the member variable, as shown in this figure. In this case, the matrix is constructed with the array of structures, and real and imaginary of elements are lined up next to each other in turns. If multiplication is conducted with AOS type matrices like this figure, the access to matrix elements cannot be contiguous, but must happen with a stride of 2. Obviously, this type of data arrangement is not desirable for fetching multiple data due to the poor data locality. So this type of multiplication process cannot fully exploit the benefit of SIMD operation in KNL because the SIMD operation need to fetching multiple data to vector processing unit. So we need to change the data structure of complex matrices to as the structure of arrays. Since our original code QEnd code adopted an AOS type data structure. In the AOS type data structure, a single complex matrix is represented with a single structure that has 2 arrays, where the one is real numbers and the other is imaginary numbers. When the multiplication of a SOA type complex matrix is conducted, the access to matrix elements can happen continuously in memory. And therefore, the performance of matrix multiplication can be enhanced with the SIMD operation using vector processing unit in KNL. And the second technique we adopted is block matrix multiplication. The block matrix multiplication is well-known performance optimization techniques for increasing the cache hit ratio. But major question is, the major question is how to determine the block size. Our answer is that it is depending on the system architecture to be used and the problem to be solved. Let's think about our case. In KNL processor, each CPU core has 32 kilobyte ARM cache. And in GV100 GPU, each streaming multiprocessor has 128 kilobyte ARM cache. And in the complex number matrix multiplication using SIMD or SIMD operations, the continuous data access occurred in 2 matrices, as we can see in here, the B and the C. So we set the block size to 32 by 32. This is 60 kilobytes because a single complex number has 2 double type variables, the real and imaginary number. Therefore, we use total 32 kilobytes for 2 matrices. In KNL, the 32 kilobyte is perfect size for the ARM cache of KNL. And GPU, 32 by 32 is perfect number to generate 1024 thread per thread block to handle a single element per single thread and map a total of 2 thread block per streaming multiprocessor. Because a single streaming multiprocessor can generate up to 2048 threads. Oh, yeah. The third technique we adopted is the thread scheduling in step 3. As I mentioned before, in our code, all the computing load of complex matrix multiplication is parallelized with OpenMP thread. However, in the matrix multiplication that applied metric blocking technique and thread parallelization together, the thread utilization efficiency can decrease. For example, if the submatrix size is 2560 by 2560 and the block size is 32 by 32 and the number of thread is 32, the matrix converted to 8 by 8 blocks matrix. Then eight rows of block should be parallelized to 32 threads. But the 80 divided by 32 is 2.5, and it is not integer number. So some threads process 3 rows of blocks, and some threads process 2 rows of blocks. Therefore, load imbalance occurred between threads. Our main idea to solve this problem is to perform multiple matrix multiplication simultaneously and adjust the number of threads used in a single matrix multiplication. In this picture, 2 or 4 multiplication are performed simultaneously, and 16 or 8 threads are used for each matrix multiplication, respectively. And compared to this situation, it can achieve the 100% thread utilization efficiency through this thread scheduling, because 8 divided by 16 or 8 is an integer number. Therefore, with this thread scheduling applied, the average thread utilization efficiency of step 3 increases from about 83% to about 100% as the XUCs increases. The fourth technique we adopted is offload computing with GPU accelerators. As it well known, more computation and less data transfer is one of the keys to efficient offload computing. So we designed a scheme of offload computing that can exploit the strengths of GPU devices. In our scheme, the step 3 is processed in the unit of submatrix columns, and computation of submatrix within a single column are executed in parallel. The computation of submatrix in single column is conducted with several submatrices that are either computed previous column or newly transferred from host. After finishing all computations, the result data is transferred to host only in the last column. Here, the number of computation in GPU is proportional to XUC square, because the number of computation is same as the number of submatrices, like this orange dot. But the number of data transfer between host and GPU is proportional to XUCs, just XUCs, because the number of data transfer from host to GPU is only 3 or 4 per column. And the number of data transfer from GPU to host, that's only happened in the last column, is number of submatrices in last column. Therefore, our scheme of offload computing would become more beneficial as the nanowire structure become longer along the X direction. For example, As the XUC increases from 2 to 1000, the number of data transfer increased from 14 to 798, but the number of computation increased from 9 to 20,999. Therefore, the ratio of data transfer to computation is about 1 to 26 when the XUC is 100. So our offload computing scheme can satisfy the more computation and less data transfer. For efficient computing, it is natural to check the utilization rate of computing resources. The NVIDIA provided the occupancy calculator as a tool that enable developers to examine the efficiency of utilization of GPU resources for their own kernel code. So we can obtain the information of the usage of GPU resources like this figure by entering the information of GPU compute capability and the -xptxs-v compile option. And when we enter this information into the occupancy calculator, the occupancy for the GPU resource is reported as a percentage. The compute capability of the NVIDIA Quadro GV100 that we used in this study is 7.0. So we set up the computing resource like this. And under this condition, a total of 2 thread blocks can be mapped to each streaming multiprocessor. And thus, all computing resources of the streaming multiprocessor are fully used. And here is the benchmark test. We use a single computing node with KNL processor and 2 GV100 GPUs. As I mentioned before, since the RGF algorithm can be parallelized to regions, we use 2 MPI processes, and each MPI process has 32 threads and one GPU. The size of target structure is 100 by 8 by 16 UCs. And this structure has a total of 102,400 atoms. And the size of the system matrix is 1,024,000 by 1,024,000. The RGF computation is performed for a single energy point, and we measured the work time taken by 4 computational steps. For examination of the effect of 4 strategies, 4 techniques, we conducted benchmark tests by classifying them into 5 cases, according to plans summarized in this table. So the results of case 1 shows that the end-to-end work time is larger than 21 hours, and almost 95% of this time is occupied by step 3. And in the test case 2, applied data restructuring, overall performance is improved by factor about 1.56 compared to case 1. And this is mostly due to the acceleration of submatrix multiplication in step 3. And these results clearly support that the AVX512 SIMD operation works more efficiently with SOA type complex matrix than AOS type. In test case 3, by applying the technique of blocked matrix multiplication, we can see the additional performance improvement. The overall simulation become faster a factor of 2.72 and 1.75 with respect to the case 1 and case 2, respectively. And the role of submatrix multiplication in step 3 is again quite obvious here. The results of case 4 show that the thread scheduling is helpful to accelerate GPU computation, RGF computation. In particularly comparing the performance of case 4 and case 3, this one, we can see that the 17% reduction of the wall time of step 3 is closely related to improvement in thread utilization efficiency, as I mentioned before, obtained through our proposed thread scheduling technique. And finally, in the case 5, where the computation load of step 3 is offloaded to GPU device, we observed the largest performance gain such that the total execution time is reduced by a factor of 6.17 compared to case 4. The acceleration driven with GPU computing becomes more remarkable in step 3, where the wall time turns out to be reduced by a factor of 14.83 compared to the case 4. And so all the 4 techniques contribute significantly to enhancing the speed of RGF, particularly the step 3. And when all the 4 techniques are applied, the entire computation can complete it in about 1 hour, while it originally takes about 21 hours. In the case 1, the step 3 takes almost 95% of the total wall time. However, in the case 5, this ratio dropped to about 37%. So within all the technique applied, the most time-consuming part of RGF computation becomes the step 1, not the step 3. That is about 47% of the total wall time. And this is last slide, the conclusion. In this study, we proposed the technical strategy to accelerate the recursive Green's function algorithm for our in-house code QN. The effective of proposed technical strategy is verified by performing elaborated benchmark tests in Manycore computing resources. And by applying the 4 strategies, we observed the wall time of entire RGF process can be reduced by a factor of about 19.3 times, which is due to the dramatic acceleration of the core numerical step, the step 3, that intensively perform multiplication of dense complex matrices. Even though we focus a specific algorithm, but the detail of the technique are quietly universal, since the multiplication of dense complex matrices is one of the most basic operations that is frequently used in a large variety of numerical problems. Yes, my presentation is finished. Thank you for your attention.
Okay, thank you very much.
Yes.
So, any questions? So the question from Professor Boku. So in your slide page 10, so did you apply NVIDIA GPU attached to KNL or separate system with ordinary Xeon hosted?
We attached 2 GPU on 1 KNL computing node.
May I have a
yes,
question
of course.
directly? So there, I think it is a very unusual strategy to attach the GPU to KNL. And don't you have any problem? For example, the KNL's PCI Express is not so strong. And don't you have any bottleneck of the communication of the attaching the GPU to KNL?
Actually, we did change some BIOS setting, something. So we tried the many. We changed the BIOS options.
So in my understanding, perhaps this is in my experience, and this is only one trial to attach a GPU to KNL. So that looks very unusual. So it's interesting. But you mean that you don't have any communication bottleneck between the GPU and the host CPU?
As I mentioned here, the data transfer is the ratio data transfer to computation is the very low.
I see.
Yeah.
Even for the GPU plus KNL.
Yes, this strategy is for the offload computing.
Yes. Okay. So there, if I'm correctly understanding that, so finally, your application running on the GPU is greatly enhanced in the performance, right?
Yes. Yes.
In
right.
page 10. So there, in that case, maybe it is not required to introduce a KNL for the even if you have a GPU only. Is it correct?
Sorry, I can't understand exactly.
So my question is that case number 5 is greatly improves the performance by the GPU acceleration offloading. So here the KNL Manycore has not so much in work and everything is offloaded to the GPU. Is it correct?
In the 4 steps, we just uploaded just this step 3. The step 1, 2, and 4 is processed in KNL.
Oh, I see. So the KNL Manycore is still contributing to the reduction of the computation time.
Yes.
Okay, thank you very much.
Yes.
So any other questions in short time? No? Okay, thanks again, Yosang.
Thank you.